oops, you can choose lots of fun. Yeah, use present. Oh, you can choose lots of fun underwater images to show where ultimately we're thinking about what is the pressure distribution on anything that's submerged. So today is the 26th. We will keep talking about this, I think, for the next 2 weeks. But today and Thursday we will go through pressure distribution, and then by the time we get to next Tuesday, we'll start talking about manometry. And so next Monday's recitation will focus on problems related to the topics that we will go over this week. So one little challenge, but it's reasonable with recitation, is that we want to go over problems from concepts that we've already covered, which hopefully makes sense to you all. We're not trying to cover new ground. As far as announcements go, one thing that I said I might do last Thursday that I didn't do yet, but I am going to try to do it either tonight or tomorrow, is reset the Clicker app connection to the class. So it's possible that you'll get kicked out, but what I will do is just let you know after I've done it, and then ask you to rejoin if you have to. I don't know that I'll lose you, but I may when I try to I'm just trying to. There's a set of steps that I didn't do exactly right when you connect it to Canvas, so that when the grading occurs each day, we're just, basically anything greater than 0 is your participation grade, that gets automatically put into the grade book, and that's not happening. So we have to import every time. We haven't done any importing yet. But after today's class, I will export those grades from Clicker, reset the connection between the iClicker and Canvas, and then upload the old all of the participation grades up to this point in the semester. So hopefully that will get updated. You'll be able to see it, and ideally we'll start with a fresh slate as well. So with the weird absences you guys were seeing for days that weren't class days, those would hopefully go away as well. So no promises, but I'm hoping. Eventually we'll move towards calculating pressure forces and calculating buoyancy forces, and talking about stability, buoyancy and stability. At the moment, I don't think there are any announcements, with the exception of the iClicker thing I just talked about. And just as a reminder, homework 2 is posted due Thursday at the start of class.
For specific weight, you can't do, like, if you wrote kilonewtons per liter or per milliliter, if you're confused. And then this part's kind of like weird and ambiguous, but there's like professional or standard ways to write your dimensions. So for instance, for specific weight, you can't do, like, if you wrote kilonewtons per liter or per milliliter, that's like not the professional or standard way to do it. It needs to be per meter cubed. Yeah, hopefully that made sense. And then, yeah, that's it.
And then just one extra thing, a couple people made this mistake, is putting units for specific gravity. Make sure to remember that specific gravity is, it's unitless. It's just relating the properties of a certain fluid to water. So we'll make sure that you don't put units for that. And then to continue on for number 5, we had a few people on number 5. So in problem number 5, it gives you the gauge pressure, but you need to find, or it gives you the gauge pressure, but you also need to add the the atmospheric pressure to get the absolute pressure for this problem. So, don't forget to do that, to add the 14.7 pounds per inches squared, because in this equation, you want the absolute pressure and not just the gauge pressure. Related to that, and also that equation was in the notes. Those equations are in the notes. Related to that, when the problem gives either imperial or metric units, make sure to put the answers in that same unit. So we had some people putting the weight in newtons. So that's not necessarily, obviously it's not technically wrong, but you want to keep it in the same units, because we didn't know how much the force was in newtons. You want to keep it in pounds if the problem stuff was given in imperial.
Cool. And then the last two you guys did super good, and these ones were hard, but you did crazy good. So just make sure that you have a free body diagram for problems like these. We didn't take points off this time because you didn't know. And then most people were super, super neat, but maybe just try to make sure we can read it. And I think that was it. Is there anything else, Alexi?
Yeah, I think in general, for homeworks going forward, definitely watch significant figures. I know, so Professor Gusev was going to put some guidance on how to do that. But in general, right, like if you get a number with 6 decimals, don't put all 6 decimals, right? There's no way you know that to that certainty. So you don't want to put that in artificially, saying you know something to that much certainty. And then also just, generally be careful with units. Try to the best way is to write out units at every single step of the problem. And that way it'll stop you from getting errors, and it'll make sure that you don't mess up somewhere in some conversion. I don't think I have anything else on that.
I'm just making a note. I wanted to add a link to the significant figures overview that I forgot to yesterday. I think I said I would during recitation, and I didn't do that. So, okay, great. A few questions have come through the chat. I guess a few of those would direct to me, so I've replied to those. But one other question. Elizabeth, yesterday at the end of recitation, and I can't remember if I captured the recording, it in the recording or not, but she asked a question about where to find for problem 3 on homework 2, part 3. So that's one of the PDF sort of problems, not the online problems. The question was about where do you find vapor pressures for different temperatures? And I had thought that there was a table or a graph in the book materials, and now it seems I stand corrected. So your guidance is to use the correct units, but here's what we'd like you to do. I was going to provide a table, and then I sort of realized, well, wait a minute. If I do that, all you're going to do is just look it up. So, because it's a fairly simple problem in a lot of ways. So what I'd like you to do, and I'll send an email to this effect a little bit after class, is identify your own source for trying to find the vapor pressure for water at, I think we said 160 degrees Fahrenheit in PSI. Okay, so, and then just identify where that source is. So in other words, if you found it online through Engineer's Toolbox or something like that, there are a variety of sources out there. Just identify, copy the link and dump it into your homework when you send it back or when you submit it. Okay, and we'll just check that link when we're ready. Any other questions before we move on to new material today? Okay, I don't see any.
Just real quick.
Yeah.
For a couple of the questions on that first homework, I didn't do sig figs because the question was given with a single figure. And I figured that was a pretty significant error. Do you want us to be rigid on that?
Yeah, from going forward, yeah, you'll need to use significant figures. So I'll provide a link in Canvas to the material that we have in the electronic book, or you can go find it yourself. It's one of the appendices essentially, but it's a pretty nice overview to just remind you what happens with significant figures when you have 1 or 2 or 3 in different numbers, and then you add, multiply, divide, whatever you do to them. How do you move forward with those? So yeah, thanks, Julie. That's reasonable up to this point, and from going forward, we'll try to enforce this a bit more and get you guys to try to get used to using those. So
Thanks.
Just quickly remember that when you go through the problem, keep this, don't round as you go through the problem. Once you get the final answer, you can write out that answer with lots more digits, and then write it again with the correct numbers.
As a reminder, we will post so we're not posting solutions right after we grade. We're going to post the solutions to all the homeworks the Friday before each exam from the last batch of homeworks. And the reason we're doing that is in case anybody gets sick and needs to turn in something late, it just gives us the opportunity to not have the solutions out there so that they can complete the assignment. So it's just a little bit of a way of providing some buffer for us. So you will see those, we will post those. It just won't happen until for a couple of weeks here. So you'll have them in plenty of time to study for the exam, but we wanted to provide this just in case we have to deal with different folks getting sick or something like that through the semester. So, all right, great. Thanks, Emma and Alexi, appreciate that. I don't know that we'll do this for every homework, but part of our point here in doing it was just to make sure that we're all developing good habits as we work through our homeworks for the rest of the semester. Okay. Right, so we're moving into a new unit here, a new module, and in this case we're thinking about, so I've got a lot of underwater images here, but essentially that's because when we go underwater, we may or may not feel it if we're just in a swimming pool, but obviously if you are a scuba diver, you will start to experience pressures at depth that are the consequence of overlying water. So our objectives here are to define and determine pressure in static fluids and pressure distributions. We're going to use the concept of manometers to write pressure equations so that we can actually work through fairly complicated systems to figure out how pressures vary, and even manometers are actually very simple ways of reading pressures in pressurized systems. And so we'll talk about how to make use of those. We will start to calculate pressure forces on submerged surfaces. And finally, this is over the next 2 weeks or so, we'll also calculate buoyancy forces and discuss stability. So what happens when when we are or are not stable. And that's really for something in particular that is partially submerged. So we think about a barge, a boat, a ship, things like that. So we can calculate the stability criteria. All right. As we see from these two pictures here, there are lots of complex shapes that occur underwater, right? We're going to start with our sort of very simple geometries to derive a lot of our equations or our relationships, but recognize that, of course, these apply even to complex shapes like a human with, a tank on their back and flippers and so forth. Whatever we can submerge, we should be able to calculate a pressure distribution on, if we can put it in a fluid. And in large part, I'm of course thinking carefully about the context of underwater, right? Okay, so I chose this picture in particular. I guess you can see 5 swimmers a long way away coming at you. But more importantly, I wanted you to just focus on the bottom of the pool. One of the things we're going to do is talk a little bit about having wedges that are underwater, and part of the reason for that is that they are 2-dimensional structures that have planes that kind of cross different dimensions or directions, X, Y, Z. So we'll talk about that in a moment. And this, I thought, was just a good example of that, a place where we have, fairly horizontal bottom to this, and then this, really nice drop off here with this ledge. So pressure is a normal force per unit area at a point in a fluid, okay? So you may be used to hearing things like when we've talked about the ideal gas law, when we've perhaps if you've had to put air in your tire, you say PSI all the time, but ultimately PSI stands for pounds per square inch, right? The square inch is an area and pounds is the force. In SI units, that might be pascals, newtons per square meter. Right? Those are the typical unit combinations that we have for pressures. So a pressure should always be a force per unit area at a particular point in the fluid. Pressure acts inward or normal to any given plane, which means that, for example, we have pressure acting on every location, every square millimeter of the bottom of this pool. which probably doesn't surprise you. And what we will eventually talk about is how that pressure varies as you move to different places, either in the fluid column, in the water column, moving up and down. These swimmers are all, swimming at the surface, but if you were to dive in, how the pressure variation changes as you go through different depths, let's say, and how it changes on the bottom of the pool based on the elevation you're at. In other words, that it might be different in the shallow location than in the deep location on the bottom of this pool. Okay, so let's start with considering a pressure force on an inclined plane, and this is this inclined plane that we're showing on the left-hand side being being submerged, okay, in, let's say, a pool or a lake for that matter. One thing I want to point out, if you're not familiar with this, this is our notation. This upside down triangle is our notation to identify a free surface, meaning the surface of the liquid where it interacts with the gas overlying. In most cases, that's air, but you could have a closed system that might have some different gas than air above a liquid. But in any event, we're going to start with a very simple situation here with this wedge. All right, so let's zoom in on this wedge a little bit. This looks complex, but it's going to get more complicated. So let's talk our way through it, and then we'll start to talk about why we're using a wedge here. So for starters, you can see that we've provided a Z direction, an X direction, and a Y direction, right? X and Y are kind of in the same horizontal plane, and Z is vertical. And so this block is the bottom of this wedge is in the XY plane, and you can see that the top surface then is sloping from this Z location down to, let's see, Y equals 0, essentially, right? So this is some length here, a Y equals 0. It has some X dimension to it, but not a Y here. In general, we're just going to give some dimensions here. The height of the left-hand side of this wedge is delta Z. So we're just using some generic notation here. And the reason is that we can start to generate some simple formulas that allow us to look at how these things relate to each other. So the first is delta Z is the height of the wedge on the left-hand side, the tallest part. It has some length in the Y dimension, delta Y, okay, going along this horizontal here. It has some width, we might say, delta X here. And then it has this hypotenuse length here, the length of this ramp or hypotenuse of a triangle here. This surface has some length, delta S, right? Now, delta S is going to become important to us because one of the things that you can see is that we're indicating a number of forces, and we'll detail those in a second. But at first, let's just start with this guy, this dashed one right here. What is this representing? It looks like it's coming from the middle. It's acting vertically down. That one should look familiar to us. Weight, exactly. Yeah, great. So this is the weight of our block. We don't know anything about its density or its specific weight yet, but it's got some volume, right? And so because it's taking up some volume and we expect it to have some density to it, we expect that there will be a force acting in the negative direction that will be the weight of the in this particular block, this inclined plane. All right, each one of these three solid arrows that's not dashed is a pressure force. Now, at the moment, we are ignoring the pressure force in the X direction, okay? We're only looking at Y and Z. And we'll talk about Y in a couple of minutes, but let's just take these three forces acting on these three faces. So you can see, let's start with the top one. The top one here, we say that we have a pressure force that is acting normal to this plane. Normal meaning that it has to act at 90 degrees. So we're starting with a simple shape because if we were to start talking about, scuba tank, right, on someone's back, that circular shape can be mathematically worked with, but it's a little more complicated. So let's just start with these couple of planes. So we've got one plane here that's sloping. We have another one that is horizontal here. And so we have a pressure force acting normal to it. And then on the left-hand side, we have this other, I'll call this a vertical plane, and we have a pressure force acting on it as well. Now, as you can expect, this inclined plane, we assume, is static. It is not moving anywhere. And therefore, all of these forces, the forces that come from all of these interactions, should all cancel each other out, that we have a hydrostatic situation. So somehow the weight and the downward component of this force are offset by this upward force, and that this force coming from the left is somehow offset by the force that is the y component of this force acting right here. Now, all of these, I've been using the term force, but where's that coming from? I indicated earlier that we have pressures acting on all of these surfaces, and these forces come from those pressures, right? So pressure is going to act normally, that is to say at a 90-degree angle, orthogonally, to every one of these faces that is on the 6 sides of this block. Wait, 5 sides. 1, 2, 3, 4, 5, right? And in this case, this one just happens to be sloping, or the force is sloping in our XYZ space simply because the face is sloping as well, all right? But each one of these forces basically comes from pressure P at some point acting across the face times its area, all right? Remember we said pressure, so we'll go through the math in a second, but I just wanted to start with this to just let you know where these forces are coming from. They come from the pressures that are acting on these faces. All right, the first one here is the first force that we have. Its magnitude is P sub S, meaning the pressure that's occurring on the S face. So we're calling this the S face, it's on the slope. Times delta X, delta S. All right, note that delta X times delta S is basically the area of this inclined plane, all right? So that pink rectangle has dimensions delta S by delta X. We multiply those together to get the area. We multiply that by the pressure that is acting on S, and we get a force, all right? Now we're gonna do the same thing on the other these other forces. P sub Z is this vertical one coming up from the bottom, and it is acting on the bottom, and the bottom has an area of delta Y times delta X, right? Delta XY, delta Y long, delta XY, delta Y long. So delta X, delta Y is the area multiplied by the pressure P sub Z gives us this force acting on the bottom. And then I'm going to skip that one for a second and just note that Py then is acting on this left-hand side, Py times the area that is acting there, all right? Now, go ahead and get your clickers and refab. We'll come back to that weight force here in a second, but what I wanted to do I have it open? Sorry, there it is. I guess I had it open from recitation yesterday. All right, so I'm going to start class now for that. I'm going to pull this over. Okay, so the question that you guys, that I want you to just wrestle with here for a sec is, what is the volume of the wedge? Is it A, delta X, delta Y, delta Z? Is it delta X, delta Y, delta S? Is it delta X, delta Y, delta Z divided by 2? Or is it D, delta X, delta Y, delta S divided by 2? So let me get going here, multiple choice, and we'll look at the results as they come in. All right, so make your choice. I'm trying to just move this guy. I can't. Oops. Okay, 45 seconds to think that through. Oh, I get it. Yeah, this is now going to be in your way. There we go. Let's get it out of your way. Sheesh. All right, but a lot of favoring C here. We have a few. We have a lone wolf on E. Not a valid answer, but I suppose you could come up with a totally different option that we didn't provide there. But I will tell you that the correct answer is there. We've got 91 responses out of, let's see, I go, I'm missing we have 102, so there should be about 99 responses. Should get about 3 more. All right. Okay, so the correct answer is indeed C, and this is the reason why I wanted to, I've forgotten I'd given you sort of the answer on the previous slide, but essentially we need the volume of this wedge to multiply by its specific weight to get that weight force. And so indeed, we are going to use that volume. So the next thing that we're going to do, I'm just going to go ahead and close this up. The next thing that we're going to do is work through the force balances here that are acting from each of these pressures and the weight, and look at how they all balance each other to come up with a few very fundamental pieces of information for us to use. And when we do that, we will need the volume. So I'm not going to go back to recalculating the volume. We've got it here, which is part of the reason I wanted to do it this way. So, all right. Get back into presentation mode. My apologies. Blank screen comes back now. Okay, great. All right, so let's move on. All right. So now this is everything revealed, and what I've left, what we skipped over before that I'll now just talk about is, here is that equation for the volume. We said delta x, delta y, delta z divided by 2, multiplied by gamma, the specific weight. So this should give us, remember this is the weight force per volume. And so this should give us the weight force acting in the vertical downward z direction. We can work out the force balances in the x, y, and z directions. First, let's go ahead and ignore the x direction. So we haven't drawn x pressures on here, or the forces related to those pressures. And the reason is that you could imagine that if I put one in that was, meeting this location here, and there was another one coming from the other side, they're both acting on exactly the same areas, so they would cancel each other out. All right, so part of the reason that we're ignoring x is that in this case, because we have the exact same area in the xz plane for both sides of this wedge, those pressure forces are going to be equal because they're at the same elevation, and they act on exactly the same areas, so they would cancel each other out. So we're just going to work in the y and z directions for our doing our force balance analysis. So because the fluid is static, and the block is static as well, we expect that the sum of the forces in the y direction are equal to 0, and the sum of the forces in the z direction are also equal to 0. Note that delta y, so one of the things I didn't note before, our angle for our inclined plane here is value theta here, right? So if we want to represent delta y, which is this length here, as a function of delta s, we can say delta s times the cosine of theta would give us delta y. Similarly, we can also say that delta z over here is equal to delta s times the sine of theta. Okay, so I'm providing that to you for the moment. We're going to use that in some substitutions in a moment, but I thought it would be easiest to just provide those to you up front because we will pull them into our analysis and not have to kind of diverge from the force part of that to just deal with geometry. Okay? All right. So let's start with the sum of the forces in the y direction. All right. First, let's start with this thing acting in the positive direction, positive y direction. So we have a pressure force, Py, whatever that pressure is that's acting on that face, multiplied by the area of that face, delta z tall by delta x wide. Then secondly, we have some y component of this force that's acting normal to the face of our wedge here. And it's going to have both a z and a y component, okay? So we've got some piece of that as well. So it's not fair to say it's ps times delta x delta s. It's going to be, we're going to have to add like a cosine or a sine to that, right, to just get the component we want. So FPY is what we'll call that force on that's coming in from the left, and FPS, or the y component of it, is what we will indicate with this blue font, noting that we want some component of that force. And of course, these two are acting in opposite directions. So for the sum of the forces in the y direction to be 0, they must offset each other, and one acting in the positive direction minus the other one acting in the opposite direction will give us 0, which means that they are going to be equal to each other. All right, so no mystery here. FPY, or the force that's that comes from the pressure acting on that left-hand side at PY, or because of PY, pressure at Y, is equal to PY delta X times delta Z. And then we subtract PS times delta X, all right, delta X here, and then times delta S times the sine of theta, all right? So delta X times delta S gave us the area of this whole thing. The sine of theta will give us the component that's working in the y direction. Now, I've grouped this in a particular way, and the reason I've grouped it this way, or put these parentheses the way I have, you may be a little bit surprised by that, because after all, delta X, delta S was the area. Why not group those? But the reason I did this is, remember, we talked about the simplification of some geometry earlier. We said that delta S times the sine of theta is also equal to delta Z. So we're going to find a simplification here. You can see that if we can replace what's in the parentheses with delta Z, we're going to be able to cancel out a delta X from both of these terms and a delta Z from both of these terms to come up with a very simple solution. So let's replace delta Z here now on the right-hand side for delta S times the sine of theta. And we have PY delta X delta Z minus PS delta X delta Z is equal to 0. I think I didn't have that earlier, but we can cancel out from these terms delta X. We can also, as it works out, cancel out delta Z. And what we are left with is that PY minus PS is equal to 0. Therefore, PY equals PS. All right, so these two pressures acting on two different planes of our block, in this case, are equal to each other. We are no longer talking about just the forces. Now we're just looking at the pressures. So the fact that these pressures are the same comes from the force balance, right? We knew the forces had to be equivalent in magnitude because they're opposite in direction. But it also turns out that in this case, PY is equal to PS. All right. Well, what will we learn if we do this in the Z direction as well? So let's go back to scratch here for a second and look at the sum of the forces in the Z, or vertical direction. Okay, so I don't know what that is. All right, so we're going to start with our upward force acting on the bottom of the wedge here, and you can see that that is a force PZ times delta X delta Y. Right, so we're going to give that green color. We're going to have the blue one again be our PS. Right now, we just need the vertical component. Right, before we were using the horizontal or the Y component. Now we're going to look at the vertical or Z component of this force acting there. And then the last thing we have, I decided to use purple for this, so we didn't reuse red, but now we've got purple for the weight force. All right, so let's again set up our force balance equation with font colors that match these indications that I've provided. So the sum of the force in the z direction will be equal to the force that is comes from the P sub z, the pressure force z, or sorry, the pressure P sub z acting on the bottom of our wedge. That's acting in the upward direction, so it's positive. Then we have some negative component of P sub the force related to this P sub s, right? So some z component would be negative. And then we have weight also acting in the negative direction, okay? So 1 up, 2 down, right? And somehow all of these have to balance for this sum of forces to be 0. All right, so let's expand these out and write them down in terms of the pressures, right? That's where we found some utility when we were evaluating the sum of the forces in the y direction. See if we can do it again here in the z direction, see if we learn something different. Spoiler alert, we will learn something different. So P sub z times delta x times delta y is this, the pressure, the force related to this pressure acting on the bottom of our wedge, okay? So there's that term. We shouldn't be too concerned about that. That should look familiar. And then the P sub s term component that we want is basically P sub s multiplied over this area, delta x times delta s. But now we multiply by cosine theta. So it is the cosine component that we want to give us the vertical component, right? And then we subtract w, oh, sorry. This again, we have another simplification going back a couple of slides. Delta s cosine theta, we said, is equal to delta y. So we're going to plug in a delta y in a moment. But let's look at our weight term. The weight term we said was gamma, the specific weight of the solid, whatever this block is made of, whatever material it's made of, multiplied by delta x, delta y, delta z, divided by 2. This, remember, is just the volume of the wedge, okay? So let's simplify a little bit here. We're going to, I've just rewritten the same equation here. So, with one simplification, sorry, to go back real quick. I did go ahead and substitute in a delta y for the delta s cosine theta, okay? So that simplification is made. So on this slide, all we have then are the 3 terms sort of simplified. The weight, the force due to P sub s acting on the slope, and then the pressure force that's acting from the bottom on in the vertical direction. All right, so let's simplify this. We can cancel out some delta x's in each one of these terms. We can also cancel out some delta y's, right? Those are common to each of these 3 terms. Now we're going to be left with a slightly different balance. That balance looks like this. The pressure at z minus the pressure at s along the slope minus gamma times delta z over 2 equals 0. Huh. What does that mean exactly? Let's rearrange this a little bit and see if this helps. P sub z, so that vertical upward pressure acting on the bottom of our block here, is equal to P sub s minus gamma delta z. All right? And if that's the case, then one thing I want to note is that there's a limit. If delta z gets really, really small, isn't it a plus? Oh, I think you're right. If I put this on the left hand, yep, sorry, this should have been a plus. Thank you. Wait, I can fix this, sort of. I have the ability to annotate. Let's see if I can do that real quick. All right, so this, yeah, apologies. This should be a plus right here. So that was bugging me as I presented it, but I'm glad you guys caught it. So the P sub z goes to the left-hand side or whatever, the right-hand side. It goes to the opposite side. What that would mean then is that all 3 of those terms would be negative. So this should have been a positive when we multiply through by a -1 to get this to be positive, this to be positive. This term should have been positive as well. So thanks for that. I do need to clear that notation to move on. Oh, before I do that though, let me just cover this point. So as delta z becomes smaller and smaller and smaller, eventually this term will basically go away, and P sub z will also be equal to P sub s, okay? So we do have an extra term here, but as we get infinitesimally smaller, or as delta z approaches 0, if essentially P sub z approaches P sub s. They become equal to each other, all right? Okay, I think I have to get rid of this before I move on, otherwise it'll stick around. So I'm going to clear all my drawings and move on to the next slide, like so. Okay. That
Professor, I have a question about the slide before.
Yeah, question.
For the arrow on the pink rectangle, isn't the x and y component, like the bottom one, should be perpendicular to, should be parallel to the y plane?
Isn't the arrow...
Not the arrow, but like yes, this part.
Yeah, so this arrow has to be normal to this plane, to the sloped plane. And what we want, we need to decompose that into two pieces, right? So there should be a vertical part and a y part, a horizontal part to it, right?
Yeah, so the y part on the bottom shouldn't be parallel to the y instead of parallel to the...
Oh, this is not indicating a component of the force. This is just indicating that it's normal. This is just showing what the angle is.
Okay.
Compared to the plane, yeah. So yeah, these aren't meant to be component forces. So
okay,
yeah, thanks.
Thank you.
Okay, so that whole exercise leads us to Pascal's law for a static fluid, which says pressures at a point in a static fluid are independent of direction, meaning that when you go take your body and jump into a swimming pool and get down to some level, and if you kind of lay out horizontally, if you can, in the pool, you know, assuming, we've all got some thickness to us, right? Some height, even if you're laying out flat. But let's just say that we're infinitesimally, kind of small. All of the pressure acting on us at that location is equal, okay? So pressures at a point in a static fluid are independent of direction. They are all occurring with the same magnitude in all directions. But I should caution by saying all directions. What I really mean is all directions inward on a point of interest, right? Or a plane of interest, or a body of interest in some way, okay? So these are two drawings, and perhaps they would be better drawn with all of these as, P2 acting on this point number 2, which is at a different elevation than all of these P1s perhaps acting on this location 1, something like that. But the idea is that these P's don't have to be the same for both places, but within each, the arrows that are all pointing to the same point have the same pressure. Okay, so all these P's are the same, and all of these P's are the same for this particular location. All right, now that's going to be helpful to us. Pressures can vary from point to point, and in fact, it will sort of depend mostly on whether we go up or down. I'll give that away to you here as a bit of a teaser for what we're about to talk about next. But when you're at a single point, all pressures, hydrostatic pressures acting on that particular point are the same, right? Okay, so now let's get into something we call hydrostatic pressure distribution. So we've been building to this, and we're going to do something similar to what we did a moment ago, but try to formalize this a little bit. All right, let's take a cube. A cube will have a delta y length, a delta x length, a delta z length. Now, I've called it a cube, which suggests that all three of these are the same value. They're all equal to each other. They don't have to be. We can have some, rectangular sort of shape if we wanted, but it's a three-dimensional rectangular image object. All right, first of all, we're going to assume that the cube is at rest. Again, hydrostatic is the key here. Secondly, we're going to say that there are pressures acting inwards on all 6 faces. Now, one thing to note is that the delta x here is the same as the delta x here, as here, as here. And delta y is the same here and here as it is on the back side as well, this back face, there and there. Those are all delta y's, regardless of the value. And delta z is the same for 1, 2, 3, 4 vertices as well. Okay, so this will help us in a moment as we work through some math, but I just wanted to take a moment to note that. And then finally, as you would expect, the weight of the cube is acting downwards, right? Vertically down. So in the z direction, in the downward z direction. All right. So let's consider the forces acting in the y direction on our cube here. And it's fine if we just assume that delta z, delta y, and delta x are all the same value. That's totally fine. So we've said that the sum of the forces in the y is equal to 0. We have a static system, so that shouldn't be a surprise. The magnitude of this force acting in the positive y direction is something we're going to call P minus del P del y times del y over 2 times delta x delta z. Okay, let's work our way through this. Delta x delta z is, of course, the area of this plane, right, on that left-hand side. And P is some pressure value. What we're doing is penalizing that. Well, P is this value in the middle, right? And then what we're going to do is we're going to subtract whatever the pressure change is with the y direction multiplied by delta y over 2. So I think I said dy earlier. This should be del P del y times delta y over 2, where delta y, remember, is this length here. So this force acting in the positive y direction is also accounting for how pressure might be changing in the y direction. On the opposite side, we're going to do something very similar, right? We're going to have, now we have P plus any del P del y. So in other words, we're accounting for how pressure is changing in the y direction times delta y over 2. In other words, that somewhere along delta y, we are going from P to whatever new pressure we might have at some point that is half delta y away from P. So that's all this is doing. It says if I have a gradient in pressure in the y direction, I'm going to multiply that gradient by this distance to give me a new pressure out here to add to P, and then that will give me the total pressure times that's acting on this face multiplied by its area, delta x delta z, and that will give me the force acting here. All right. So in this case, we said P minus whatever our pressure gradient is times some distance to get over to that location if we had a pressure gradient in the y direction. All right, now, as you can expect, when we write these out, we're going to say that the force acting from the left, this one over here, minus the force acting from the right, which is in the negative y direction, is going to be equal to 0. So all we've done is now formally put these into an equation to fill out this sum of the forces in the y is equal to 0. And when we take the next step, we basically find the p's will cancel out, right? A plus p, a minus p. We have delta x, delta z, delta x, delta z. Those will cancel. What we end up with is that del p del y, the pressure change in the y direction, is equal to 0. Okay? Now, you may have trusted me if I said that the change of pressure in the y direction is equal to 0, but we needed to prove it. And part of the reason for that is that we're going to see how this is different in another direction. So I'm giving that away a little bit. But let's just take a more practical approach to this. If I go down to a certain elevation in a pool, so let's say that I actually don't know if the rec center on campus is open and we could go swim in the Ralphie pool, but let's say we could. And we go down 3 feet, all right? And I can kind of hold myself horizontal, and laid out at 3 feet of depth, right? So it's 3 feet of water above me. No matter where on my body, I try to make a measurement, all parts of the top of my body are 3 feet from the top, meaning that there's no pressure distribution. When we move horizontally in a fluid, we should have no pressure distribution as long as the overlying fluid or liquid depth doesn't change, okay? And it turns out this is the same for the x direction. So I'm going to skip the step of going through this whole thing for the x to just note that the same thing would be true if we substituted an x for a y and thought about what was happening sort of into the screen and out of the screen on this plane and this back plane compared to y. So same thing would happen. But there's something different going on for z. So let's spend a moment thinking about that. So here's our summary that when we go through this y, or if we went through it for x, the sum of the forces in the y direction equaling 0 yields that there is no pressure gradient in the y direction. Similarly, we can go through the exercise for x and find that there's no pressure gradient in the x direction either. Okay, I think we'll probably wrap up with this concept here. All right, so let's consider what happens in the z direction. Now, unlike x and y, gravity works in the z direction, and that's our biggest difference here, okay? So we have our cube again. We're going to assume delta y, delta x, and delta z are all the same value. So we have our cube, and pressure is noted at this value right in the middle of our cube, okay? So P is some pressure at that value, right? When we start to put these together, we see that we have two forces acting. One is P plus del P del Z times delta Z over 2 would give us the force that's acting in this negative direction on this plane is this value P plus whatever a dP dZ is multiplied by this length to get us to that face, okay? Similarly, from the bottom, we now have P minus del P del Z times del Z over 2, which basically says, hey, from this pressure, I'm going to go down to this location where this face is, which is delta Z over 2 length away, and I need to subtract whatever, wherever I should be for del P del Z as pressure is changing in the Z direction. And that is also multiplied by the face area, delta X, delta Y. All right. And we've left this off to the side, but of course the weight, I just didn't want to have it, right on top of the other arrow here that's acting upwards. The weight, of course, is also acting downward, and it has a value of delta X, delta Y, delta Z, so the 3 dimensions, because this is cubic, multiplied by the specific weight, the weight times volume. So that gives, or weight per volume rather, multiplied by the volume will give us the weight acting in the negative direction. So again, some of the forces in the Z direction are equal to 0, and we can put these two together and say that, 3 together now. So now we have this pressure force acting on top. So that guy goes here, it's acting in the negative direction. The one that's acting upward is this positive term right here. And then we subtract the weight as well. And it is because of that gravitational weight that if we go to simplify this all out, we end up with del P del Z is equal to a negative gamma. All right. What this means is that the change in pressure as we increase our depth is equal to, or Z gets more negative, right, is equal to the magnitude gamma. All right. Gamma, remember, is rho times G. So it will be dependent on the density, in this case, of our fluid, not necessarily, well, we are, I know we've talked about this being a cube. Let's talk about it being a cube of fluid rather than a cube in fluid, all right? And therefore, that negative gamma is the specific weight of water. So it's the density of water multiplied by the gravitational acceleration, so rho times g. But this is a very simple, easy thing to think about, and we can conceptualize it. We're going to start to make use of it as we start to think about how forces are distributed through depth. Okay, so similar to what we said a few slides ago when we considered the x and the y direction, now the sum of the forces in the z direction equals 0. That yields this del P del Z, or the change in pressure with depth, is a function, or the rate of change is minus gamma, which is the specific weight of whatever your fluid is. Okay. All right. So let's take two depth locations here. So you can see we've got our free surface here at the top. We're in some red liquid for some reason, but in any event, we can consider a location here above a datum. Okay, so some Z1 location. It has some pressure 1 value, and then we can go to this second location up here. So it has some height above our datum Z2, and it has some pressure 2 at that location. H is equal to the distance between Z1, the elevation of, Z2, the elevation at Z2 minus the elevation at Z1, all right? So just the difference between those. Now, what we want to look at is trying to integrate the pressure change across this depth between Z1 and Z2, all right? So the first thing we do is we note, as we did on the previous couple of slides, the change of pressure. And by the way, I've gone from a partial derivative now to a definitive derivative, like give that ordinary derivative here, to basically say that dP dz is equal to minus gamma. All right, so no partials here. And what that means is that we could rearrange this and say that the change in pressure is equal to minus gamma times the change in elevation. Oh, now this is useful, right? Because we've been talking a little bit about delta x and delta y, and now we have dp and dz. But z's, that is these specific elevations, are values we should have. And gamma is a value, particularly if we're underwater, we should know what gamma is. We can go look it up for a certain temperature, right? And in SI units, that'll be in newtons per cubic meter, right? If it's water at 4 degrees centigrade, it's 9,810 newtons per cubic meter, right? That's something we could look up. So we could populate this value by looking it up if we knew what fluid it was, and maybe its temperature. We could at least assume a temperature. And we could probably measure this and actually get a value. Now, real quick, before we move on, let's think about this for a second. I told you that the units, let's see if I can type this out real quick in my annotation. Okay, so this is going to be in dimensions, gamma's in dimensions, let me put let's just do the dimensional analysis. Let's not worry about the sign. So this is going to be force per length. I don't think I can put in a superscript, so I'm going to use the little caret here. Force per length cubed, all right? And then we're going to multiply it by just length, right? So from a dimensional perspective, we should end up with force per length squared, right? The length cubed in the denominator, when we multiply it by a length in the numerator, will give us just length squared in the denominator, or force length to the minus 2, or force per length squared, which is exactly what we should expect for a pressure, right? So that should work out for us. The change in pressure is equal to the change in elevation within our fluid column here, and we multiply that by the specific weight of the fluid. All right, I think I need to clear that. Actually, let me move forward here and clear it in a second. Now, we said that we wanted to integrate over these changes, so these differences. So let's go ahead and do that. Real simple integration here. We're going to integrate dp from P1 to P2, right? At this location at 1, we have some P1. At location number 2, we have some P2. So the integral of dp from P1 to P2 will be equal to minus gamma. This is just a constant, so we're going to pull that out, right? And then we integrate on the right-hand side, we integrate dz from Z1 to Z2, right? Again, from an elevation at Z1 to an elevation at Z2. And when we do that, we come up with, on the left-hand side, P2 minus P1 is equal to minus gamma times our specific weight multiplied by Z2 minus Z1, okay? And I need to get rid of those. Sorry, my text there, clear all drawings before I move on to the next slide, or it'll stick around. Okay, so the pressure difference is equal to minus gamma times the elevation difference. That seems hugely useful, in part because we can, perhaps if we can't measure the pressures directly, we can measure the elevations, and we know we can look up gamma, our specific weight. Okay, so we can rewrite this now as this equation here. So let me just go back real quick. Let's divide through by gamma on both sides and put the z's to the, and then combine by location, right? So P1 over gamma plus Z1, be on the left-hand side, is equal to what we call P2 over gamma plus Z2 on the right-hand side. So real quick, just to go back, all I did was divide through by gamma, and then I grouped the ones on one side and the twos on the other side, okay? So P1 over gamma plus Z1 is equal to P2 over gamma plus Z2. What this says then is that an offset in Z, right, is made up by a change in P, or really P over gamma. And so this sum is equal to this sum. So when we go from Z1 to Z2, we are increasing Z, right? Z2 is some value greater than Z1. That means that P1 must be a higher value than P2 because these sums have to work out. They have to be equal to each other. The other thing that means then is that basically P over gamma plus Z is a constant. Wherever we are throughout this fluid column, this liquid column, P over gamma plus Z is constant. Meaning if we move down, then pressure goes up and elevation goes down. If we move up, Z goes up and P goes down. Okay, they offset each other perfectly so that we can always come up with these sums working out. The other way to write this, if we go back to what we had on the previous slide, was P2 minus P1 is equal to minus gamma times Z2 minus Z1. Ultimately, another way of expressing that is to say that P1 is equal to P2 plus gamma times H. Now, H, remember, was Z2 minus Z1. So essentially, all we're doing is replacing this with H, just the distance between these two elevations, and multiplying or moving this P2 over to the right-hand side, and then changing all of the signs, right, to get everything to be positive instead of everything being negative. So P1, this pressure right here, is equal to whatever pressure we have at 2 plus this height and the pressure that comes with changing this height by our fluid specific weight. Okay? All right, this is a really critical concept because this basically is hydrostatic pressure. And we will build on this on Thursday to talk a little bit about how we put this to use and how we predict changes then with depth, because this really tells us that for every Z, there is some P over gamma, and as we move around, those two are going to offset each other to give us a constant value. All right, with that, my wrap up is, remember that homework 2 is posted due on Thursday before class. I think technically I have it at 12:50.